Now can you hear me? Okay. Well, let me check something. Oh, now you can hear me? Okay. Great. Let's see, we have Zarkia. Oh, hi, William. Thanks for logging in. Do you have any questions? You don't have to ask questions, but since we're here. Hi, Anthony. Okay, Euler circuits and Hamilton circuits. All right, let's look at a couple of questions from the, what's it called? The sample questions from D2L. Hopefully everybody knows where to find those. Let's start with Euler circuits and Hamilton circuits, and then we'll go take Zarkia's question about cryptography. So, I'm gonna try to switch here. Let's see, to this screen. Okay, can you hear me now? about now? Is it any better? Now you don't hear anything? Okay, how about now? Can you hear me? No? Oh, much better? It's working? Okay. All right, I think maybe I figured it out then. Okay. All right, so the question was about Euler circuits and Hamilton circuits, and this is something that if you know it, it's really going to help you on the third exam. So I think it's definitely a good question to go over. I'm going to look at, first of all, everybody needs to remember the difference between the two, okay? You're going to mess up a bunch of questions if you don't. So Euler circuits versus Hamilton circuits. Can you see what I'm writing? Let's just make sure. Everybody can see that I wrote Euler circuits. It's blurry. Okay. Sorry to hear that. Is it readable? I have no idea what. A little blurry. Oh, that's a bummer. Okay. Let's see. Do you know how to up the resolution in the video stream? Okay, is it better? You might need to refresh, I guess. Okay, I'm gonna keep going. Sorry about my dog. Luke, come here. All right, so I'm gonna keep going because everybody's time is precious. So we're going to say the one thing that this is going to save you points, to remember Euler circuits versus Hamilton circuits, and we'll get into exactly what they mean in a second. But basically, if you can remember, Euler starts with E, which means you have to visit every edge, E for edge. Okay? Now, what is there in a graph? Because we're talking about graphs when we're talking about circuits. In graph theory, there are only two things. There are vertices, which are the little dots, okay? And then there are the edges, which join the vertices. So when you think of an Euler circuit, You think of something that has to, first of all, circuits are kind of what you would imagine. They have to start and end at the same place. They come back to where they started. So let's say I have a circuit. I want to make a circuit. I'm going to start at a particular vertex. I'm going to travel along several edges. And I'm going to come back to where I started. I have a circuit. Now, the key to an Euler circuit is that you visit every edge once, okay, and only once. So Hamilton circuits, on the other hand, they have to do with the other thing, the vertices. So Hamilton circuits, you're going to visit every vertex once, except for the one that you start on, of course, because you're going to end up back at it, so you kind of visit it twice. But other than that, you're going to visit every vertex. So remember, every edge, E for Euler, every vertex, Hamilton. Okay? So as an example, and by the way, we often name our vertices with letters, so A, B, C, D, E. Okay, what I've drawn here, it started with the vertex A, and it went to vertex B, and then C, and then D, and then E, and then back to A. And I said it's a circuit because it travels from where it starts, it travels right back to it. So it kind of makes a loop. So it's definitely a circuit, but who can tell me, is it an Euler circuit? Type it into the chat bar, is it an Euler circuit, yes or no? So remember, Euler means edge, so did it visit every edge exactly once? Yes, okay, you're correct. And what about, is it a Hamilton circuit? Without reusing the same edges, that's right, only once. Yeah, and it's also a Hamilton circuit because it visited every vertex exactly once. Okay, so an example of a question from your review that asks about Euler or Hamilton circuits would be number 33. Okay, and it looks like this. It's got 6 vertices. Labeled A, B, C, D, E, F. And they're connected like this. And like this. Okay, it says determine whether the sequence of vertices is an Euler circuit. So determine whether, and then they give you this. A goes to B, goes to C, goes to D, goes to E, goes to F, goes to A, is an Euler circuit. Okay. So let's follow along here. So A to B, and then B to C, and then C to D, and then D to E, and then E to F, and then F to A. So let's take this one step at a time. Okay, is it a circuit? So what does it have to be a circuit? Well, basically, it just has to follow a bunch of edges and start and end at the same place. So this is a circuit. It starts at A and it ends at A. Okay, so this is a circuit. And now, what does it mean to be an Euler circuit? Hold on one sec. Okay, sorry about that. I'm back. That's right. It has to visit every edge to be an Euler circuit. So is this one an Euler circuit? You're right. It's not an Euler circuit, and it's just because it skipped over some edges, right? What did it skip over? It skipped over these. E to A and A to C and E to C. 3 edges were missing, so the answer to that question would be no. Good job. You guys are getting the idea, I can tell. Okay, now on the other hand, would that be an example of a Hamilton circuit? That's not what the question asked, but if they did, would that be an example of a Hamilton circuit? Yes, and you're correct, Zarkia. Why is it a Hamilton circuit? It does touch every vertex, that's right. It's a circuit, so it starts and ends at the same vertex, and it hits every point in between. There is no need for it to go, cover every edge, because that's not what Hamilton circuits are about. Okay? All right. Another thing you need to know about Euler circuits in particular is how to know that they exist. It's actually easy to predict whether a graph can have an Euler circuit. Not as easy with Hamilton circuits. But with an Euler circuit, you can always tell if you're going to be able to construct an Euler circuit. So in this case, for number 33, we said that the circuit that we were given was not one. Does anyone know the trick to determine if, in fact, one does exist? Very good, William. William's got it. Oops. So he said if there's an even amount of edges per vertex. That's right. That's called the degree of the vertex. The degree of a vertex is the number of edges that touch it. And what he said is basically that you have to have all vertices must have even degree to have an Euler circuit. And that sounds kind of abstract, but if you think about it, it makes sense. An Euler circuit means that you cover every edge exactly once. Now, let's imagine that here's a vertex somewhere on some graph, right? And in order to visit that vertex, or I should put it another way, to cover these 2 edges, we have to come into the vertex and we have to leave it without going over the same edge twice. So the only way that that can happen is if we have an even number of edges coming in. It could be 4, right? Because we could come in and leave and then come in and leave again. But it has to be an even number of edges. So in this case, again, in number 33, they didn't actually ask the question. But in this case, I could tell you whether or not, even though this wasn't an Euler circuit, I can tell you whether or not this has one, because I can look at the degree of each of these vertices. So vertex A has a degree of 4 because there are 4 edges touching it. B2, C4, D2, E4, and F2. So even though this particular sequence of vertices they gave us didn't make an Euler circuit, we know that that one exists. If we searched long enough, we could find one. Okay, and number 34 on your review, it asks you about that. So all you need to do is look for even degree. Okay. Who knows what Flurrys algorithm is? Do you know what Flurrys algorithm is used for? Yeah, that's right. Very good. So Flurry's algorithm, so what we've talked about is what an Euler circuit is. And you need to know that Euler means edge. We talked about how to know if a graph has an Euler circuit by looking at the degrees. And now, how do we actually find one? And that's what Flurry's algorithm is about. It sounds fancy, but it's not. So let's look at an example. I'm gonna pull one up here. I'll just draw it. Okay, so this is actually number 35 on your review, and it gives you a graph that looks like this. Okay, so here's my graph, and we're supposed to use Flurry's algorithm to find an Euler circuit beginning and ending at the vertex A. Okay, so we're supposed to find an Euler circuit beginning and ending at A. And we're supposed to use Flurry's algorithm. Okay, so to understand the instructions for Flurry's algorithm, you need to know one term, and William just mentioned it. It's called a cut edge. A cut edge is an edge that if you remove it, it separates the graph into two separate pieces. So for example, let's suppose we had this graph. Good questions, Anthony. The way that you determine if you have a cut edge is if it's going to create two separate graphs. So for example, on this graph that I just drew, not the one that we have in our problem, but this new one that I just drew, this would be a cut edge, because if I were to remove it, I would have two separate components. What's that called when a graph has two separate components with no edge between them? Does anyone know that term? Two separate components with no edge joining them, like when I erased this edge right here. You remember what that's called? There's going to be a lot of vocabulary on the test. I would recommend making some flashcards. Disconnected graph, good. So if you remove a particular edge and the result is a disconnected graph, then you know that was a cut edge. Okay, so this edge here was a cut edge because if I removed it, we would then get a disconnected graph. Okay, so what Flurrys algorithm says is basically to create an Euler circuit. You're going to walk around imagine yourself walking around the graph and kind of removing edges as you go. An Euler circuit covers every edge, so we want to just walk around and hit every edge. Just be careful that if you have a choice between an edge that is a cut edge and one that's not, that you always choose the one that's not for your next step. Does that make sense, I hope? So if we're looking to start at side A and create an Euler circuit, all we're going to do, and I'm not actually going to erase edges, I'm just going to highlight the ones that I choose. So from A, I can either choose A to E or A to B to be the start of my circuit. It doesn't matter, because if I remove either of these, it's not going to cause my graph to be disconnected. In other words, neither of these is a cut edge. So I'm just going to go A to B. And then at B now, we can either go B to E, or we can go B to D, or we can go B to C. But remembering that this line that I highlighted, the edge rather that I highlighted, has essentially been removed. One of these three, B to D, or B to D, or B to C, one of those is actually now a cut edge. Which one is it? Anybody know? Remember, A to B is gone now. So out of the remaining graph, which one of these, if I removed it, would cause us to have a disconnected graph? So if I removed this one, we would not have a disconnected graph, right? If I removed this one, we would not have a disconnected graph. But if I remove this one, keeping in mind that these are gone, we would have a disconnected graph. So what that means is that in order to construct my Euler circuit, I either need to go B to C or B to D. Either one is fine. I like to go in alphabetical order if I can. It just makes it easier. And so I'm going to go B to C. And then is C to D is the only way I can go. So I'm going to go C to D. And then from D to B is the only way I can go. And then from B to E, and then from E to A. So let me number these. We went 1, 2, 3, 4, 5, and then 6. Okay, so the Euler circuit that we found using Flurrys algorithm, it's not the only one possible, but it was A to B to C to D to B to E and back to A. Hello, Katina, thanks for coming. Okay, so how do we feel about using Flurrys algorithm? I mean, it makes sense that you wouldn't want to create a cut edge, because then you're going to be stuck. Oh, the time difference in Ecuador, that's funny. You're going to be stuck over on one of the graphs, and you won't be able to create a circuit, right? So that's all Flurrys algorithm means. And by the way, I kind of, shame on me, I missed an opportunity here because I should have pointed out that we know that an Euler circuit exists because of the degrees, right? Vertex A is degree 2, E is degree 2, D is degree 2, 2, and 4. So we have even degrees, so we knew that there had to be an Euler circuit. So if that's the case, then Flurrys algorithm will always give you an Euler circuit. Okay? All right, and then unfortunately with Hamilton circuits, not as easy to know if there's going to be a Hamilton circuit, but there are some situations where you know that you will or you won't. In particular, if a graph is complete, you know you'll have a Hamilton circuit. So some facts to know. Hamilton circuit. If a graph is complete, there is a Hamilton circuit. So that begs the question, what does complete mean? We haven't talked about complete. Does anyone remember what the term complete means in graph theory? Nobody remembers? So all it means is that between any two vertices they're joined by a single edge. So for example, if very good, Sarkia. So this is not complete. Okay, let's call this graph number 1. Number 1 is not complete. But graph number 2, we can always take an incomplete graph and we can fix it, because all we have to do is make sure that everybody's joined to everybody else. Okay? So this one would be complete. Now, you might notice that graph number 1 has a Hamilton circuit, right? Because you can definitely visit every vertex once and come back to the beginning. So does number 2. In fact, it's the same. So that's why I'm saying that it's a little trickier with the Hamilton circuit. Knowing that a graph is complete suffices to guarantee that it will have one, but just because it's not complete doesn't mean that it doesn't. It still could, and sometimes you just have to experiment with it to figure it out. Okay. If a graph has a vertex of degree 1, it will not have a Hamilton circuit. Now I'm thinking about that and I'm wondering if there's a special case where it would. Hold on just a second. Yeah, so if a graph has a vertex of degree 1, it will not have a Hamilton circuit. Sorry, my handwriting is a little messy today. And the example that I'm thinking of is on number 38 on your sample questions. It's got a graph that looks like this. And it asks whether the graph has a Hamilton circuit. And if you think about it, because of this guy being kind of isolated out here, having only degree 1, the only way to visit him is to go out to him and then come back. And when you do that, you're going to hit this blackened in vertex twice. Okay, and you're only supposed to hit every vertex once. So that's the reason why this cannot have a Hamilton circuit. Okay, so even though it's not easy to know for sure whether graphs in general have Hamilton circuits, there are some tips where if it's complete, you know that it will, and if it has a degree 1 vertex, you know that it won't. Does anyone know how to calculate in a complete graph how many different Hamilton circuits there are? So let's say you have a Hamilton, a complete graph with n vertices. How many different Hamilton circuits are there? That's right, Jake. That's when they use n-1 factorial. So that little exclamation mark. n-1 factorial. So the reason I wanted to mention that is just to make sure everybody remembers how to calculate a factorial. So let's look at that real quick. So for example, if I asked you how many Hamilton circuits are in the graph that we just drew a minute ago. Okay, so this is a complete graph and it has 4 vertices. So according to the formula n equals 4, we want to find n-1 factorial. And so we're talking about 3, because 4 minus 1 is 3, factorial. What does 3 factorial tell you to do? What is 3 factorial telling you to do? Remember, it's telling you to multiply something. What's it telling you to multiply? So that factorial very good, Jake. Yes, so it's multiplying all the numbers from 3 down to 1. 3 times 2 times 1, or 1 times 2 times 3. The order doesn't really matter, but so that's going to be 6. So there would be 6 different Hamilton circuits within this particular graph. Okay, now don't worry, there's usually a factorial button on your calculator. Let me see if I can pull, yeah, see here on your calculator you have n factorial, so you don't actually have to remember what it means, but that's what it means. Okay, so any other questions about Hamilton or Euler circuits before we go back and talk about the cryptography question? And I just want to remind everyone there are sample questions in D2L, very similar to the types of questions you will see. It does not, the sample questions do not include the Katina has a question. That is a Hamiltonian circle of size 3. Are you talking about the graph, Katina? That's right here on the screen. Oh, what's your question, D'Anthony? Yes. So D'Anthony's question was, do the Hamiltonian circuits have to touch all the vertices before it goes back to the ending vertex, which is also the beginning vertex? And the answer is yes. It has to touch each one exactly once. And again, before we wrap up our conversation about them, remember this: Euler is every edge starts with an E once, and so Hamilton's going to be what the other thing, the vertex, every vertex once. Okay. All right, so Zarkia, you had mentioned that you had a question about the cryptography. So was there a particular question or just in general? One thing I want everyone to know about the cryptography questions, you know, where you have Bob, is that the step-by-step instructions will be provided, and there's only going to be like one, maybe two questions on a test, but the instructions for the steps as they're given in the ebook, they will appear on the test. So you know, where it says to calculate, it gives you like the letters and what they stand for, and asks you, given this is this, and let me see if I can find it. Hold on. So it says like choose two prime numbers, P and Q, and compute the modulus N. And all of that, those steps are actually going to appear exactly as they appear in the book. So let me try to pull that up. Can. I know my ebook wasn't working recently, so hoping I can pull it up. Oh, yay. Looks like it's working. Okay, so this is what I was talking about. Let me just grab this here. Okay, there are, for example, for RSA cryptography, we have these steps, and I want you to know that those will be provided on the test. Katina wants open notes. Oh, okay. So Zarkia, you're okay with it since the steps are given? Yeah. I do not expect you to memorize that at all. Okay. Did anyone else then? I guess I answered her question. Anyone have any other questions? If not, I'm going to wrap it up. I want to thank you guys for logging in. I want to remind you that you can send me your Ask My Instructor questions. And if in the past there was a delay, I guess they've changed the email setup on the Ask My Instructor. So when I hit reply, it doesn't go to you. So sometimes I've made that mistake, and if you don't hear from me within 24 hours, it's not because I haven't responded. So what I would encourage you to do is to just email me directly and say, Ms. Hearn, I didn't get your response. But I have been going back through and double checking to make sure. Some of you may have received some Ask My Instructor responses late, and I forwarded it to you because I realized I sent it to the wrong, I hit reply and you can't anymore, so just kind of a bummer. But anyway, you can email me your questions. If you don't want to use the Ask My Instructor function, some people take a picture and email me as an attachment, the picture of the problem. But we're wrapping it up. It's almost over, and oh, you're very welcome. I'm glad you were here. So just don't be shy, okay? In these last few days, if something comes up, you need to contact me right away. Okay. All right, guys, I'm going to log off. And thank you again for logging in. I really appreciate you being here. And good luck with everything. And don't be a stranger. Bye-bye.